Okay, so this will be part 2. We're going to call this part 2. And we're going to do the example number 4. Read example number 4. Example number 4. At 1 p.m. on January 15th, 1919, an unseasonably warm day, a 90-foot high, 90-foot diameter cylindrical metal tank in which the Puritan Distilling Company stored molasses at the corner of Foster and Commercial Streets in Boston's North End exploded. Molasses flooded the streets 30 feet deep, trapping pedestrians and horses, knocking down buildings and oozing into homes. This must have been a sight. It was eventually tracked all over town and even made its way into the suburbs via trolley cars and people's shoes. It took weeks to clean up. Okay, so that's the backstory. So in other words, you have a cylindrical tank, which a radius of 45 feet with a height of 90 feet. A, given that the tank was full of molasses weighing 100 pounds per cubic feet, 100 pounds per cubic, so this is the weight density. What was the total force exerted by the molasses on the bottom of the tank at the time it ruptured? Okay. The pressure in this situation, I think the book gives you okay, so the book in the middle of page 429 tells you that the fluid pressure is basically the weight density times the height. You'll normally see this represented as rho GH, okay? So this would be just the actual volume, the actual density times the gravitational constant, okay? But the book is using this, so we'll stick with this, okay? So we have WGH, so the pressure at the end here, so the depth would be what? Height would be what? 90 feet, right? So this is 90 feet, and I have, this is my weight density times 90 feet. So I'm going to have 9,000 pounds per square feet, because one of these cancels out. So this is feet squared. I just need to find the area of the bottom here, right? Because it's feet squared, right? I need to find out how many feet squared there are. So the feet squared would be what? 90, what was the area there? Pi r squared, right? Pi r squared. If you do that, you get 57 million pounds. Lots of pounds. So all that pressure was exerting on the bottom, and it basically just fell through, right? Exerted so much pressure, you rusted out, I don't know, whatever, but it was not able to handle the weight, and it just bursted out. B, what was the total force against the bottom 1 foot wide band of the tank wall? Okay, so we're going to look at the bottom 1 foot tank wall here. Okay. And we're going to cut this into infinitesimally small bands, small little bands here. So we're going to do a delta y here, right? Delta y. And each band, right, you're going to have pressure across that whole strip. Does that make sense? You understand what I'm saying? Right? So that strip, I need to find out the area of that strip. Okay, so the area of that strip, if I take that strip, that's going to look like this. I'm going to cut it in half, I'm going to flop it open, right? And cut it in half and flop it open. Then it's going to look like this with delta y. And this is going to be what? How long is this? That's the circumference of this, right? So circumference was 40, so the r was 45, so it's going to be 90 pi, 2 pi r, right? The circumference around the circle, right? Around the circle. Okay, so the area that it's exerting is going to be this. Okay. So that. So blah, blah, blah. So this was the last one. We're done with that. So the area is 90 pi times delta y. Okay. And how deep is this? So if I call, I need to know the pressure, right? Pressure is going to be from the whatever, the height here from here to wherever, right? If I call that y, right? So it's going to be 89 plus y? No, it's just y, right? I'm going to go to y, but y is going to go from where to where? Nope. Because I'm not interested in this stuff here. I'm interested from here to here, right? 89 to 90.
So like, wouldn't 89 to 90 be at the top of, like, why wouldn't it count up from the bottom, I guess?
I'm calling this 0. I'm calling this
So
90.
it doesn't matter what direction it goes.
No, it doesn't matter. Okay. And then we got to do the 100, so we have to put that in there. Right?
100 is coming from the weight.
Mm-hmm. And that's it, I think. You just pull the 90 pi, 9,000 pi out. 9,000 pi, 89 to 90, y dy. 90 pi, 1/2 y squared, 90 to 89. And 2.5 million. If you do that.
Would it or would it not make a difference if you just said like 0 to 1 instead of 89 to 90? Because it's constant, right? So does it make a
Okay, so then this would be different, right? Because if I go call this 0 and I call this 1, so the height would be 90 minus y, right? And you go from 0 to 1, right? So yeah, so this would be different. This would be 90 minus y now, instead of y. Because you're looking at the pressure starts from here and it's exerting down, right? It's the height from here that matters, really. Right? Because it's the depth that you're worried about, depth. Because pressure is the depth times the water density, and not the weight density, right? Okay. Okay. And we will call it a day.